So we're looking at section A1 here, torque. We're going to have three objectives. First, to discuss the difference between a point mass and an extended object, where torque is applied. To calculate the torque acting on an object, and to define and apply rotational equilibrium and net torque. So to start this, let's first look at the definition of torque. This is just a general definition I gave here. Force applied at a given distance from a fixed point, and this traditionally causes a rotation. Now, we're assuming that it's a pin joint right here. There's a pin or a rod going through here, like into the page or out of the page, and this is able to swing freely. This object would traditionally rotate. Now, it could be fixed in a wall. The wall could be here, right? You could have a wall like this where it's fixed, and then that's a cantilever beam, and there's still torque acting on it, but it really wouldn't rotate freely there. It would start to bend, and we call those bending moments. For now, though, we're going to take a look just simply at torque and see what happens. So, our formula for torque is RF sine theta. R is the actual distance between the rotating axis, which is here, and where the force is applied, over here. So obviously this object rotates. This is fixed right here. There's a pin going through, or a bolt if you want to, and this can swing around it though. You can think of this as a door frame from a bird's eye view. This would be the hinge of the door. This is where the handle of the door would be. You'd push the door and the door would sweep open like that. So R again is the distance between the actual axis of rotation and the force of where it's applied. F is the actual value or magnitude of the force, and theta is the angle between where the force's vector is and the line drawn along the distance. So for the case of this, if we called this theta, it would have the same effect. And the reason being is that these two angles are supplementary, and we know that two angles that are supplementary have the same sine value. Okay, and this is something from your trig class that you may or may not know yet, but sine of, say, 70 is equal to the sine of 110. Again, because those two angles, these are in degrees, those two angles there would be considered supplementary. They add up to 180. Something to write down as a note that we should really understand is that torque, like velocity and force, it's a vector quantity. So we can assume a certain direction. So what I do is this. I assume that a positive sign is given to a force that alone would cause an object to rotate counterclockwise. And a negative sign is given if that force would cause it to rotate clockwise. And this is just an adoption that physicists and engineers have used for a long time. So in this case right here, this force right here acting on this object where this pin is located would cause this object to move down, right? Push down on the object, it bends down, but it would just rotate like this. And this is clockwise. So clockwise, again, clockwise is a negative torque, and counterclockwise is considered a positive torque. Now, we'll see here that this is clearly an extended object. It's not a point mass. In the past, we've been able to model things that travel as projectiles or even objects as point masses. So we looked at all the forces acting on those objects, but we didn't look at the torque. We didn't think about the fact that it has some desire to rotate or some what we call moment of inertia. So in this case, this is an extended object because we're looking at its dimension, or we're utilizing its dimension and recognizing that a force acts at a distance which causes a torque. Okay, the torque is caused by the force acting. And there's several things that we're going to make some correlations about now. But before we do that, we should also point out the fact that the units here are Newton times meters, which is very similar to work. If you recall work, the formula for work was F d cos theta, and this was measured in newtons, and this was measured in meters, and we called work units joules. A Newton meter was considered a joule when we looked at work and energy. Well, in this case, it's still just a Newton meter. It's not actually written as a joule. It's not an amount of energy in the torque. And what we'll see and what you might recognize is that in the United States, pound-feet are used. Pound-feet, because pound is the force and feet is the length. The first thing we have to do before we can make these correlations is define what's called the lever arm. And the lever arm is the perpendicular distance from the axis of rotation, right? In this case, in this diagram here, there's the axis of rotation. The perpendicular distance between the axis of rotation and a line drawn along the direction of the force. Well, here's the force being applied this way. Here's the actual distance between the axis of rotation and the force. The lever arm is from here all the way to here, a perpendicular line, when it's given in the diagram up here, so it's a little more obvious, but a perpendicular line between, again, the axis of rotation and the force itself. Down here would be the line between here and here, again shown up here, and the same thing between the axis of rotation and the force. That's the lever arm. And what you'll recognize here is that the lever arm turns out to be just r sine theta. And it's not obvious and easy to see this, but we can prove it with a quick triangle. So let's take a look at a diagram. Let's say that we have, let's say we've got an object with an end that can rotate over here, and we've got a force applied to that object, like so. We know that we'll call this angle theta right here. And we want to figure out what the lever arm would be in this scenario. Well, we have to extend the force direction infinitely. So let's go ahead and extend that. So here's the force. Let's extend that direction. Extend that direction. And then what we need to recognize is that, well, we're looking for the perpendicular distance. If I were to draw a line from here to here, this is not perpendicular to this line. If I draw a line from here to here, it's not perpendicular to this line. But if I draw the line from here directly to here, there's that right angle. So really, I'm drawing this line in right here, which makes this a right angle, which makes this a right triangle. Now we can label things. If you recall, this is R right here. Right? This is the length between the axis of rotation and where the force is applied. That's R. And if I know that value is theta right there, then I can say right away off the bat, well, this is just going to be R sine theta. And how do I know that? Well, I know that because if I call this, let's say for now I call this, instead of R sine theta, call it some variable, or call it, I'm going to call it lever arm, LA. Doesn't matter what I call it. That is the lever arm, but let's prove that that lever arm is equal to R sine theta. So we could say that the lever arm is opposite, right? It's opposite this angle in the triangle, and this is the hypotenuse. Opposite of hypotenuse is the sine function. So we could say that the sine of theta equals the lever arm, which is the opposite, over the hypotenuse. So how do you get the lever arm by itself? Multiply both sides by r, which brings r up here, multiply here, those cancel. So the lever arm is just r sine theta. So in this section, we're going to continually use this formula. Tau equals r f sine theta. And you can always use that formula. But if for some reason you're given some information, you're told the lever arm is some distance, we could really recognize that the lever arm is the product of these two factors in that in that equation. So I could rewrite this if I want to as tau equals f r sine theta, which is the same thing because obviously multiplication is commutative. And since this is defined as a lever arm, the torque acting on an object is really the force acting times the lever arm. Okay, I'll put lever for now, but times the lever arm. Again, we're going to use RF sine theta, but if for some reason you know what the lever arm length is, you can use that formula as well. Some things to note here, or one thing at least to note, is this. If you look at these diagrams on the right here, let's zoom in on these so we can see them a little bit better. This should say degrees, not infinity here. If we look at these diagrams here, we're going to see that the maximum torque is achieved when the angle is 90 degrees. And then as the angle gets closer and closer to zero, you get less and less torque. And it's kind of obvious, and it's hard to show in a video. I could show it to you more demonstrating. But think about like a wrench. If you have a wrench, you're going to want to push perpendicular to the orientation of the wrench itself. If the wrench, if you push in the same direction as the length of the wrench, it's not going to go anywhere. So imagine, for the sake of this, that this force was not here. Okay, imagine that force is not there on the right. If I applied a force like this, I'll put F app for applied. If I apply a force to the wrench that way, it's not going to rotate that bolt. If anything, it's just going to push on the head of the bolt, maybe causing the head of the bolt to snap off. But that doesn't cause any rotation, because if you think about it, the angle between these is 0 degrees. Here's the length, or the direction, of the actual lever arm in this case, if that were the applied force. And the applied force is on top of that, which makes the angle 0. So what we'll see is that as the angle approaches 0, the torque approaches 0. So if we wanted to write down some sort of a relationship here, what we can do is we could say that as theta decreases from 90 degrees to 0 degrees, tau decreases from the maximum amount of torque to zero torque. Start by looking at example 1 here. Which of the following hands produces more torque on the bolt in the figure there? Well, it looks like we have a horizontal wrench and we have a hand pulling down vertically. So we know that the angle here is going to be 90 degrees. And we're trying to compare the two torques. So let's first find the torque of object or person A. Person A acts at a distance away with a given force times the sine of whatever the angle is, which is 90. And a lot of you have recognized by now that the sine of 90 is indeed 1. So the torque involved is just the distance away, which is 1 meter, times the force applied, which is 20 newtons. So it's going to be 20 newton meters. Now, because this is going to cause it to rotate clockwise, I should write that this is negative 20 newton meters. And the torque acting, or as a result of the second person pulling, well, the second person is at a different distance of 2 meters, but pulling with half of the force, 10 newtons. Well, double the distance, half the force, have the same outcome. It's still going to be 20 newton meters. And again, because it's rotating clockwise, we give it a negative sign. It's negative 20 newton meters. So in the end, which is producing more torque? The answer is the same. They're both producing negative 20 newton meters of torque. So for example 2, we're trying to find the net torque acting on this massless object. And as a result of finding the net torque, we can determine, will it actually end up moving? And if so, in which direction? And recognize that it's a massless object, and that's important because if it weren't massless, it would have its own what's called moment of inertia. And moment of inertia is an easier way of saying that, like, you know what? If the pin is right here, which it is, this object has more mass to the left than it does to the right, if it had mass. So it would naturally want to fall this way on its own. It's like sitting on a seesaw. The bigger person is over here. It's like this is the smaller person over here, really. Okay, so it's a bigger person or the bigger part of the beam on the left. But because it's massless, we do not really have to worry about any of this. Okay, it's no necessity or no need to consider the moment of inertia involved because it's massless. So to do that, if we want to find the net torque, we could simply say, tau net equals the sum of the taus. So we have 2 of them here. So tau 1 plus tau 2. Now we have to start looking at this. Look at force 1 first. This force is acting down, but on the left side of the fulcrum, so it causes it to rotate this way, which is counterclockwise. But the other one acts the other way, which is clockwise, again, because if you think about it, this is pushing down, which would cause this end to rotate like this and be clockwise. So this is going to be clockwise, which we were considering negative earlier, so we can say that this sign in the middle, after you put the plus there in the first time for tau net, you can rewrite it like this. Tau net equals R1 F1 sine theta 1 minus R2 F2 sine theta 2. Again, it's minus because that part would cause a clockwise rotation. I could put here minus if I wanted to, but honestly it doesn't matter. At the end, you just need to have a minus here for sure because this is causing a different rotation than this. They're kind of balancing each other out, or trying to balance. So we can go ahead and plug in some numbers here. Right? The net torque acting is the distance from the fulcrum, 4 meters. Again, we're looking at the one over here on the left. This is 4 meters away, times the amount of force applied, 20 newtons. And then the sine of theta, well, it's 90 degrees, and the sine of 90 is 1, so I don't really need to write anything there. And then for this second one over here, F2, it's acting at a distance of 3 meters away with a force of 15 newtons at an angle, though, of 30 degrees. And if you know something about this, you're going to recognize that obviously here we're going to have more positive torque than negative torque, and that's kind of obvious mathematically because this is 80, this is 45 times some fraction. Remember, sine of any angle is always going to be a fraction. The highest value a sine function could have is 1, and that's when it's the sine of 90. The sine of 30 happens to be 1/2. So this is going to be half of 45, which is 22.5. So we get as a result here 80 minus 22.5 Newton meters. So we have 57.5 Newton meters. And that's the net torque acting on this object. Well, if there is a net torque, if the net torque had been 0, that means that these two torques are balanced and this object wouldn't actually rotate. It would stay still. It would be in rotational equilibrium. But because there is a net torque acting on it, and the net torque happens to be positive, it's going to rotate. And which way is it going to rotate? It'll rotate whichever way we defined. Well, we defined positive earlier, right? This was our positive torque because this caused a rotation that was counterclockwise. This was the clockwise rotation. So since we get a positive answer, it's going to be counterclockwise. So example 4 says that to determine the location where the 10 Newton force should be acting in order to produce rotational equilibrium on the massless rod. So in this case, we don't know the value of R for the 10 Newton force. Then the follow-up question is the rod also in a state of force equilibrium? Well, we want to produce rotational equilibrium, which means that there is no net torque acting. The torques balance each other. Well, start by looking at this. First of all, this one's going to cause a clockwise rotation. This is going to cause a clockwise rotation. This is going to cause a counterclockwise rotation. So we have what looks like 2 negative torques, both clockwise, and 1 positive torque, which is counterclockwise. So let's go ahead and write our equation here. We know the net torque acting on this has to equal 0 because there's going to be rotational equilibrium. It's not going to rotate. So we have to look at the 3 different torques. We've got obviously torque 1 plus torque 2 plus torque 3, and that equals 0. Let's go left to right. So torque 1, we'll start. We have that recognize that this first force here, we'll call this F1, is 10 units from the pivot. Here's the pivot. This is 10 meters away, and that's the force itself. So this is going to be R F sine theta. Now, because that's clockwise, we have to apply a negative sign for that. Next, we look at the second force. This force acts 6 meters away, produces counterclockwise torque, which is positive, and the angle is 90 degrees, which simplifies things. So this is positive, and again, 6 meters away times a force of 25 newtons. And I don't need sine theta, because again, it's sine 90, which happens to be 1. And then last but not least, this other force out here on the right, it acts at a distance r from the fulcrum, which we're trying to determine, but at an angle of 45 degrees. Now remember that because it's clockwise, we're going to apply a negative sign for this last torque, and it's going to be negative. Now the distance away from the axis of rotation is r times the force applied, which is 10 newtons, times the sine of 45 degrees. This whole thing equals 0. So we have an equation here. Don't forget about this negative sign here and this negative sign over here. This is positive. And all we have to do is go ahead and solve for r. You can rearrange it, go through the process, solve for r. In this case, for r, you would end up getting 2.84 meters. Again, treat this like any other algebraic expression. This is a number, combine like terms, move it over, and then divide by whatever this number turns out to be. 2.84 meters. So clearly this diagram is not drawn to scale, right? If this is 6 meters and this is 2.84, that doesn't look right. So you can't assume that a diagram is drawn to scale just because you're given some, unknown length r here. So that's the location that it should be, 2.84 meters. So really probably like around here if it were drawn to scale. The follow-up to this question says, is the rod also in a state of force equilibrium? Well, for rotational equilibrium, we said the net torque equals 0. To get force equilibrium, the net force has to equal 0. So we have to really find the net force in the x direction and the net force in the y direction. And we don't know if it's equal to 0. We have to figure it out. And then if it is equal to 0, we know that is in force equilibrium. So we have to go back to our diagram for a moment. I can see clearly here that this is acting up and to the right, so that's got some x component to the right. This is acting down and to the left, that's got an x component to the left. This is only acting down, so it's only got a y component. This is acting to the right, as we said, so it's positive. This is acting to the left, so force-wise, it's negative. So here I'm going to use 15 cos 60, and then I'm going to have a minus 10 cos 45. Okay, again, 15 is the actual force, newtons, times the cosine of 60 degrees. And that's positive because that was pushing up and to the right, and the right is positive in the x. and then minus the other portion, which is going to be 10 times the cosine of 45. That will give us a number. That number is 0.43 newtons. So it's almost at a state of equilibrium horizontally. Almost, right? 0.43 newtons. In the y direction, though, now we have to go take a look at the y direction and recognize that this is acting up and to the right, so it is acting up, positive y. This is acting all down, so that's all y. There's no need for cosines or sines components. This, though, is acting down and to the left, so again, it's acting down, but only a component of it. So this will be 15 sine 60 minus 25 minus 10 sine 45. So let's go ahead and write all three of those. So again, we have 15 newtons times the sine of 60 for the first force on the left. That's acting up. The middle force, which is 25 newtons, is just acting directly down. And then the last force is acting down, but it's at an angle. It's at an angle of 45 degrees. So that's going to be our net force in the y direction, which turns out to be negative 19.1 newtons. So we can see that clearly this object is not in force equilibrium, because these would have to both equal 0 for that to be true, and clearly these are not 0. So what does that mean to us? It means that, you know what? The bolt that's located where the pivot is, or the pin, whatever you want to call it, is going to feel a force pulling it down. Even though it's not rotating, it's going to feel that force pulling down due to this value right here. So that bolt or that pin, it could fail due to like what we call shear stress acting on the bolt. And mainly this would be from the y direction. This is pretty much insignificant here. But again, this is the location that it should be placed at, that last force that we didn't know, so that it provides rotational equilibrium or a net torque of 0, even though the net force is clearly not 0 as seen here and here.